Welcome to the lesson on section 10.5, the logistic equation. In this lesson, you'll learn how to examine slope fields for logistic growth and how to solve a logistic differential equation. Until now, you've always used the exponential equation y equals y0 times e to the kt to represent population growth. But what does this equation imply about population growth that may not be realistic in most situations? Take a look at the graph of an exponential function. As time increases to infinity, so does the population. In reality, population growth slows and population numbers tend to level out over time because of limitations in the environment. The logistic model for population growth accounts for these flaws in the basic exponential model. There are two constants: lowercase k, which is sometimes called the growth rate, and capital K, called the carrying capacity. The carrying capacity is the maximum population that can be sustained over the long run. You might recall that we've already looked at a slope field for a logistic equation. If you look back at your sheet for section 10.2 on direction fields, you'll see that you graphed the differential equation dy dx equals 0.08y times 1 minus y over 1,000 in wind plot in class a few days ago. In this example, the total number of people infected with a virus grows in a logistic pattern. An initial population of 10 people have the virus, and the number of people infected increases with a growth rate of 1.78. In the long run, an estimated 5,000 people will be infected. In Part A, we'll write a logistic model for this situation. Using the formula from the previous page, the rate of change of the population with respect to time is proportional to the current population times the quantity 1 minus the population divided by the carrying capacity. The carrying capacity, capital K, is 5,000, and lowercase k, the growth rate, is 1.78. Before we solve this differential equation, let's think about what the slope field would look like. The slopes would be 0 when the population P is 0 or 5,000. It makes sense that the population growth would be 0 if the infected population was 0. Since the rate of infection is 0 when the infected population is 5,000, this means that the infected population will level out when it reaches 5,000. That's why 5,000 is considered to be the carrying capacity. Let's continue solving the differential equation, separating by multiplying and dividing. Multiply the numerator and denominator of the left side by 5,000 to simplify the complex fraction, and take the integral of both sides. The integral on the left side requires partial fraction decomposition. I need a fraction with a denominator of p and another with a denominator of 5,000 minus p. Multiply both sides of this equation by the common denominator and substitute values of p to solve for a and b. Notice that the value of lowercase k, the growth factor, had no influence over the values of a and b in our partial fractions. So now we need to integrate 1 over p plus 1 over 5,000 minus p. In future solutions of the logistic differential equation, we can assume that the partial fractions will be 1 over p and 1 over the carrying capacity minus p, like in this one. Anti-differentiating, I get the natural log of p minus the natural log of 5,000 minus p equals 1.78t plus c. Technically, the left side should include absolute value signs, but negative populations wouldn't make sense in this situation, and we won't consider cases in which the number of infected is greater than the carrying capacity. Use a law of logs to combine on the left side. Rewrite the equation in exponential form and rewrite e to the c as the constant capital A. Take the reciprocal of both sides. In this case, a would really become 1 over a, but I don't know what it is yet anyway, so whether I call it a or 1 over a, it's still some unknown constant multiplier. Separate the left side into 5,000 over p minus p over p, and add 1 to both sides. Isolating p by making a diagonal swap gives p equals 5,000 over 1 plus a e to the negative 1.78t. Notice that it's the carrying capacity over 1 plus a e to the negative growth rate times t. Because this topic is likely to show up on the AP exam at most once or twice, I'll leave it up to you to decide whether you just want to memorize this as a separate formula or solve using the steps we just applied when you need to find a logistic model. To solve for A, we need to use the initial infected population of 10 people. A equals 499. So the number of infected people at time t can be found by p equals 5,000 over 1 plus 499 e to the negative 1.78t. For part B, we need to determine the time it will take for the infected population to reach 1,000 people. Substitute 1,000 for the population. Multiply 1.499 e to the negative 1.78t and divide by 1,000. Subtract 1. Divide by 499. Take the natural log of both sides and divide to finish solving for t. It will take about 2.7 weeks for the infected population to reach 1,000 people. Now let's look at a solution for that logistic equation from the previous lesson. Notice that the growth rate is 0.08 and the carrying capacity is 1,000. Multiply and divide to separate, and multiply the left side by 1,000 over 1,000 to simplify the complex fraction. Partial fraction decomposition will result in 1 over p plus 1 over 1,000 minus p. Integrating both sides, I get the natural log of p minus the natural log of 1,000 minus p is equal to 0.08 t plus c, and so on. If we follow the same steps as in the previous example, we'll end up with p equals 1,000 over 1 plus a e to the negative 0.08 t. This concludes the lesson on section 10.5, the logistic equation.